In addition to defining the derivative and the integral in terms of geometry, we can also define them in terms of change. So these are notes again instead of examples. This is derivative and integral. And now we're going to give the change definition. The derivative is the instantaneous rate of change of a function. The most easy to comprehend change that we have is in terms of velocity and position. So let's say we imagine so we know a person's position over time how fast is their position changing at a particular instant. So this would be called also what is their instantaneous velocity. And especially for these practical problems, it's going to be really important to have the units. These units are always going to be the y-axis units divided by the x-axis units. And this is because slope, which remember is associated with the derivative, is divided x. So a helpful way to visualize this is using an example of a person moving back and forth. This is over time, so the blue graph right here, that's giving his position on this little ruler here. So like right there, he's at 0 meters, he's at 0 on the position graph. Velocity is that little red arrow that we're looking at right here. It's just how fast is he moving? What's his velocity in meters per second as he goes along? This green graph is acceleration, although we're not going to be working with it right now. So what we want to know is we want to know what's moving man's instantaneous velocity, what's his rate of change of position. Let's say when he hits this tree. So he's going along, basically this little velocity that's tracking his change in position over change in time. That's really what the derivative of position is, its velocity, and then right there when he hits the tree, just a little bit further, right there when he hits the tree, if we want to know what his change in position is, his instantaneous velocity at this point, we can look right down here in the blue. Let's move him back just a little bit. There we go. What's the slope of the tangent line to the blue curve right now? Well, it looks like it's going to be a flat line, slope of 0. And lo and behold, when we look on the velocity graph, right there, the value of the velocity graph is 0. So when we're talking about a derivative as a rate of change, this is what we're talking about. We have his position in meters. The derivative is his change in position, meters per second, his velocity. The integral goes the other way. If we have a function that gives a rate of change, the integral is the accumulation of that change. So to give an example using moving man again, If we know a person's velocity over time, what is their total change in position? This is also saying distance traveled. And the units for this, they're going to be the y-axis units times the x-axis units. And this is because area is height, which is y, times base, which is x. Looking back at moving man, what we're really looking at here, instead of going from position to velocity, is we know something about moving man's velocity. What's his total change in position? So velocity is a rate. Let's say like right here, from 12 seconds to 14 seconds. I know right here on this red graph that moving man is moving at 3.5 meters per second for these 2 seconds. So that means that over the course of these 2 seconds, if we find the area under this curve, so this width is 2, this height is 3.5, so this area right here is 7, that means that his change in position should be positive 7 meters. And lo and behold, if we look at what his position is at 14 seconds, ta-da, he's gone an additional 7 meters. So the idea with the integral is that if we know this rate of change over how long that rate of change has been going on for, then that'll give us the total change up here on the position graph. You can see that the integral and the derivative are very tightly linked. Basically, one goes from position to velocity, the other from velocity to position. And in fact, they are very tightly linked. The derivative and the integral are inverses. Meaning they undo each other. Just like multiplication and division are inverses. Let's look at some examples using this change definition. So here we have a graph of velocity. And given this velocity graph, would you use the derivative or the integral to estimate the distance traveled from 5 to 7 seconds? So take a minute to think about that. What do you think? We will be using the integral because remember, velocity is giving us a rate of change, so meters per second. We know that distance is in meters, so to get back to meters, we're going to be taking the integral, getting back to the total change, the total distance traveled. So we'll be using the integral. On the graph, we want to draw a geometric representation of the distance traveled. Remember, this is the integral we said right up here. So go ahead, draw something on here that represents the integral from 5 to 7. Remember, the integral is the area under the curve, so we're looking at the area under the curve from 5 to 7. Now we want to estimate the distance traveled. So the distance traveled was the integral, was the area under the curve from 5 to 7. So we're just going to divide that up into little boxes just like we did before. Use that to estimate. So we've got 1, 2, 3, 4, 5 little boxes. And then this is a little less than half a box. That's a little less than half a box. So if we put these together, we're going to be almost to 6, but not quite. So approximately, let's call it 5.8 or something like that. Really, we could say probably anywhere between probably about 5.5 to probably 6.5, somewhere in there. It's sort of an approximation. However, it's going to be very, very important to have the units. So this is area. Units are going to be meters per second times seconds. Seconds cancel out. Or approximately 5.8 meters. For this next example, I'd like you to take a look at it and then pause the video and try to do it on your own. When you're ready, start the video again and I'll show you the answers that I have. Go ahead and pause the video now. Okay, so to estimate the rate of change, so the keyword here is rate of change of velocity with respect to time at t equals 4 seconds, to use the integral or derivative. Remember from what we were working with earlier that rate of change right here, we're looking at the derivative. So this would be the derivative. The derivative is represented by the slope of the tangent line. So we're going to draw a tangent line at t equals 4 seconds. So t equals 4 right here. Draw a line that just brushes. Something like that. Now notice that yours might have been a little more tilted up, a little more tilted down. That's why we're going to spend a whole year working on this stuff so that we can get this really precise. But for now, we just want an estimate. So we're going to estimate the slope of this line for part C. Change in y is 1. Change in x is 1. So we're looking for slope. Change in y over change in x approximately equals 1 over 1 or 1. Now, this could be anywhere between 0.5 to, with these it's actually really hard to tell. So as long as it's positive and it's not too big, it's going to be fine. However, we need to make sure that we have units. So the units are going to be y units, meters per second, divided by, because we're doing division over here, divided by seconds. This is the same as seconds over 1, so it's 1 meter per second. Dividing by a fraction is the same as multiplying by a reciprocal. So there are 2 seconds in the bottom, 1 meter per second squared. Those are the units for acceleration, incidentally, which, if we looked at the moving man example, was the next level down from velocity. That makes a certain amount of sense. But this is what we're looking at when we're finding our units. Slope, derivative, we're going to do the y units divided by the x units. Up here, area, multiply the 2 units.